Hello, and welcome to our presentation. I'm Jiacheng Zhang from Purdue University. Today, I'd like to talk about the uncertainty estimation of PIV and PTV-based pressure using velocity uncertainty. The PIV and PTV-based pressure reconstruction has drawn significant attention as it can provide pressure field measurement without invasively altering the flow. The velocity-based pressure reconstruction starts with calculating the pressure gradients from the measured velocity field using the Navier-Stokes momentum equation. Then the pressure gradients are spatially integrated to obtain the pressure fields. The integration can be carried using different methods, including the path integration algorithms, solving the pressure Poisson equation, and the least squares methods. Previous studies have shown that the accuracy of the reconstructed pressure can be affected by several factors. The pressure gradient calculation can be affected by the velocity arrow level, the spatial and temporal resolutions, the arrow profile, and the formulations used for calculating the material acceleration. In addition, the accuracy of the integrated pressure fields can be affected by the algorithm used for the pressure gradient integration, the pressure boundary condition setup, as well as the size, the shape, and the dimension of the domain. Therefore, it's necessary and at the same time very challenging to estimate the uncertainty in the reconstructed pressure fields. The recent developments of the uncertainty quantification algorithms for PIV and PTV allow for the local and instantaneous uncertainty estimation of the velocity measurement. We propose to use the velocity uncertainty to estimate the pressure uncertainty. First, with the velocity uncertainty estimated for the PIV and PTV measurements, the covariance matrix of the velocity field is constructed. The autocorrelation and the component-wise correlation is considered and reflected as the off-diagonal elements in the covariance matrix. The arrow propagation from velocity to pressure gradient is approximated as a linear propagation by dropping the nonlinear arrow terms, therefore allowing a simplified linear uncertainty propagation as indicated by the equation here. Similar to the previous work by Aziliad et al., the arrow propagation from pressure gradients to the pressure field is treated as a linear propagation, and the pressure uncertainty in the form of a covariance matrix is obtained using the presented linear equation. The velocity uncertainty-based pressure uncertainty estimation was firstly tested using synthetic flow fields generated based on the 2D pulsatile flow between two parallel plates. Only the bottom half of the channel was used in the analysis to save computational efforts. Gaussian noise was added to the synthetic velocity fields based on predefined noise levels and was proportional to the local velocity magnitude. The standard deviation of the added velocity noise was used as the standard velocity uncertainty. The method was firstly applied to the test case with uncorrelated velocity noise at 10% noise level, as suggested by the histograms. The predicted pressure uncertainty matched with the pressure arrow as suggested by the RMS values for the reconstruction using each individual integration method. Moreover, the spatial distribution of the predicted pressure uncertainty was consistent with the pressure arrows. The pressure arrow level was lower near the wall at the bottom, where the velocity noise was lower, and higher in the core flow. The predicted uncertainties also capture the different distributions of pressure arrow from different reconstruction methods. The weighted least squares and the generalized least squares methods better contain the high error region in the core flow therefore leading to lower overall pressure error level. The obtained pressure uncertainty also predicted the temporal variation of the pressure error as suggested by the plot below. We have also tested the uncertainty estimation method with different noise levels. The predicted uncertainty matched with the corresponding pressure error for most of the noise levels. The uncertainty underestimated the pressure errors for the cases with very low noise levels for the weighted least squares and the generalized least squares methods, which was due to the bias error that was not accounted for by the proposed uncertainty estimation method. Furthermore, the proposed method was tested on correlated velocity noise. The velocity noise was designed to be spatially, temporally, or component-wise correlated. The spatial and temporal autocorrelation was defined as a Gaussian function of the spatial and temporal separation, respectively. The error analysis, as shown in the figures, suggested that stronger spatial correlation led to greater pressure error and uncertainty, while the temporal autocorrelation had insignificant effect on the pressure reconstruction for this dataset. The effect of the component-wise correlation was not significant unless the correlation was greater than 0.5, which was unlikely to be seen in real experiments. Next, the uncertainty estimation was applied to the experimental PIV of vortex ring flow. The PIV images were processed using Prana and Davis with standard cross-correlation and iterative window deformation. The velocity fields obtained using 3D tomographic PIV were used as the ground truth for the error analysis. The velocity uncertainty was obtained from moment of correlation and image matching methods for the Prana results, and the correlation statistics method was used for obtaining the uncertainty for the Davis results. As suggested by the histograms, the velocity uncertainties underpredicted the velocity errors. As shown in the spatial distributions, the velocity uncertainties were higher in the vortex course, which was consistent with the errors. However, the spatial distributions of the velocity uncertainties were more uniform across the field compared to the velocity errors. To account for the spatial autocorrelation of the velocity errors due to window overlap of the PIV processing, the spatial autocorrelation was modeled as a Gaussian function of the spatial separation, and the correlation coefficient equals the window overlap for neighboring velocity measurements. The obtained pressure uncertainty, as suggested in the histograms, was lower than the velocity errors in terms of the RMS values. This is potentially caused by the underestimation of the velocity uncertainty compared to the velocity errors. As suggested in the spatial distributions, the pressure uncertainty shared the same trend with the pressure error as they both increased from the reference point on the left center to the right of the domain. Similar to the comparison between the velocity errors and the velocity uncertainties, the pressure uncertainties were more uniform than the corresponding errors. Furthermore, the uncertainty estimation was applied to volumetric PTV measurement of a laminar pipe flow. The velocity fields were obtained using triangulation or IPR reconstruction. The velocity was interpolated to Cartesian grid with inverse distance weighting. The velocity uncertainty was firstly estimated on the particle locations, then linearly propagated to the grid nodes since the IDW interpolation is a linear process. Here we are comparing the velocity and pressure errors and the uncertainty histograms. The RMS uncertainties matched well with the RMS errors for both velocity and the pressure reconstructed using each method. The spatial distributions of the velocity and pressure errors and uncertainties are presented here. From the spatial distributions, it can be seen that the velocity errors and the velocity uncertainties were more uniform across the domain compared to the distribution of the pressure error and uncertainties. And the pressure errors and the predicted uncertainties were lowest near the center of the inflow plane, where the reference point was imposed during the pressure reconstruction. Also, the spatial distribution of the uncertainty matched with the corresponding error distribution. In summary, we introduced a framework to estimate the uncertainty of the reconstructed pressure field based on the velocity uncertainty. The method was validated with synthetic flow fields and applied to the experimental measurement using PIV and PTV. The analysis showed that the method was able to predict the effects of several factors that can affect the pressure reconstruction accuracy, including the velocity error level, velocity autocorrelation, the pressure integration method, and the boundary condition. We can also see that the reliability of the obtained pressure uncertainty depends on the accuracy of the velocity uncertainty. If the velocity uncertainty underestimates the velocity error, the predicted pressure uncertainty is likely to be underestimated. The future work will include applying the method to volumetric PIV measurement. Thank you, and here are the references included in this presentation.